Baalbek has the largest stones that were ever quarried in human history, the largest stones that were lifted, stacked, and transported.
For years, Baalbek was treated as a site that historians already understood. That confidence disappeared when a new investigation revealed details that did not match any familiar explanation. According to researchers who worked there, the deeper they looked, the more the evidence pushed back. Something at the site refused to fit the old story, and the findings forced the team to confront a possibility they never expected.
Here you get an idea that just the size of this thing is outrageous, and in relation.
The AI that saw what historians missed. For a long time, Baalbek sat under a confident explanation. The common belief was that the Romans built everything at the site. Historians trusted this idea because it fitted their expectations. The Romans had the tools, the workforce, and the engineering knowledge.
Baalbek is one of those places where you have different people over millennia building their shrines, their temples to their particular.
According to several researchers, any contradiction was brushed aside as a measurement error or a misreading. That certainty began to crack as new studies arrived. Tool marks on the stones did not match Bronze Age or Iron Age chisels. They also did not match any tool tradition the team could recognize. Physics tests kept showing that the known transport methods could not move stones that weighed hundreds of tons.
Jupiter Temple must be 60 or 70 feet tall. They're so high. And then from up here, you can look back across at Bacchus Temple.
Roman archives offered no record of any project that involved shaping or lifting blocks of that size. The main platform even pointed toward a sky pattern that did not belong to the Roman era. According to some field workers, the site felt like a puzzle that could no longer be held together by old assumptions. The contradictions reached a point where the team needed a new approach. This was when they turned to a pattern recognition AI. It was originally designed for engineering analysis and forensic stone studies. The team taught it to identify microscopic signatures in metal and stone.
Other scientific tests that can be done, like carbon-14 dating. The problem with a test like that is that it's what we call a destructive analysis.
To interpret radar scans and to compare structural geometry against long-term sky models. It had already been used on Roman bridges, Mayan pyramids, and several ancient Chinese foundations. Internal reports stated that the group trusted it because it did not create theories on its own. It only handled data and tested that data against known construction styles. Before they committed to it, the team held several meetings where they debated whether it was time to let a machine recheck everything. According to some researchers present at those meetings, they finally agreed because the traditional explanations were no longer holding together. Once the decision was made,
today with the new technologies that are being developed.
So it's very much 21st century technology.
They loaded every file they had into the system. The toolmark studies added thousands of close scans, hundreds of clear photographs, and basic chemical readings from the stone surfaces. The geological work contributed radar scans of the ground, simple soil tests, mineral notes from the quarry, and maps that showed pressure points in the bedrock. Every file was uploaded exactly as it was collected. According to the team, this was the only way to make sure their expectations did not influence the results. The AI studied the material in stages. It compared tool marks to known Old World traditions, assigned probability scores to each construction phase, and built a timeline using weathering depth and erosion patterns. It tested the alignment data against every sky model in its library.
Not really surprising from a creation perspective, but is a big mystery. Not only.
When it finished, it combined all results into a single analysis that highlighted conflicts and anomalies. The first major contradiction appeared at once. The foundational megaliths did not match Roman engineering practice. The AI detected no Roman iron chisel signatures and no Roman proportional systems. It identified placement and load patterns that did not belong to classical engineering. The sky alignment also pointed to an era the Romans did not work with. According to reports from those present during the review, the room went silent. Some asked for the files to be checked again. Others insisted there had to be a mistake. The system labeled the foundation stones as non-Roman and non-classical. With that, the accepted story collapsed, and the team was forced to ask a much harder question.
Megalithic sites on the planet, this has been misidentified as possibly being...
If the Romans did not cut the stones, then who did? To find the answer, the team began studying the tool marks again through the AI's lens, and this led to an even stranger discovery. Tool marks from a lost engineering system. After the AI ruled out Roman involvement, the team returned to the stones with a new sense of urgency. According to several researchers, they expected the next step to clear up the confusion, but the opposite happened. The AI showed that the cuts in the limestone did not look like the result of hand tools at all. The surfaces were unusually smooth.
You can see some really good examples of Egyptian-style tool marks here, almost like saws with diamond-tipped saws.
The channels followed clean lines, and the depth of each mark remained almost identical from start to finish. This level of control did not match the irregular blows that bronze or iron chisels should leave behind. The team agreed that something else had shaped these stones. The microscopic scans supported this concern. They revealed channels that kept the same width throughout their entire length. They revealed cuts that followed precise paths with no sign of hammer pitting or chisel vibration. The AI compared these marks to every tool pattern in its database. It tested Roman chisels, Phoenician wedges, Assyrian picks, and even older Neolithic traditions. None of them matched.
Once again, the incredible erosion patterns that we see with the megalithic works at the quarry at Baalbek.
The system then flagged several similarities to industrial cutting techniques that used flowing water mixed with abrasive material. These methods used steady streams of water to guide the cut, while particles in the water did the actual grinding. According to unverified reports from inside the team, this was the first moment when the room grew tense. The match was not exact, but it was close enough to raise serious questions. Chemical tests added another layer of surprise. The AI highlighted the presence of quartz sand and small pieces of corundum on the cut surfaces. These minerals were harder than limestone and could act as strong abrasives when moved through water. They were also not natural to the area, which suggested intentional importation. Some members of the team believed this pointed to a planned and organized cutting process rather than simple experimentation. Nothing in the older explanations accounted for this kind of preparation. The AI then focused on the quarry floor.
The stones at Baalbek, the three that are still in the ground, to me that betrays the fact that the Romans gave up. It's like you've got three in the wall already. Why are there three more in the ground that you didn't take out?
It identified evidence that the builders had used a freeze and thaw extraction method. According to the system, the workers would have carved narrow trenches around a block, filled those trenches with water, and allowed winter temperatures to freeze it. The AI detected patterned vertical cracking and fracture lines that matched known freeze and thaw signatures. It also highlighted shallow channels in the quarry floor that appeared to guide water movement. Similar techniques existed in prehistoric Scandinavian and early Chinese quarries, although none of those examples operated at the scale seen at Baalbek. Together, the water-assisted cutting and freeze-based extraction created a cutting system that did not belong to any known culture in the region. The Romans had never used such methods, and no ancient Levantine group had either. According to the team, the marks pointed to a process that was scientific, controlled, and carefully planned. This implied the presence of a skilled engineering group. It also left the researchers uneasy. If the cutting was this advanced, then the task of moving the stones would raise even greater problems. Transport physics. The cutting alone had shocked the team, but according to several researchers, the real fear began when they turned to the transport problem. If the stones were shaped with such advanced methods, then moving them should reveal even more. The AI was given the task immediately, and the team expected at least one traditional idea to survive the tests. That hope disappeared quickly. The AI began by converting every known variable into usable data. It used the exact weight of each block, the strength limits of wooden rollers, the tensile capacity of ancient ropes, the slope of the terrain, soil friction measurements, the contact area beneath each stone, and weather conditions predicted from historical climate records. According to internal notes, the system was instructed to assume perfect coordination in the best possible conditions. The team wanted to be fair. They wanted to know if brute force could work in any scenario. The system ran more than 10,000 simulations. It changed roller spacing, adjusted rope counts, tested different roller materials, shifted path directions, and examined sledges with and without lubrication. It even tested shallow incline adjustments to see if the ground itself could support the load. The first results were brutal. Wooden rollers failed almost immediately. Under weights that reached 800 to 1,600 tons, the rollers flattened and splintered. The friction created so much heat that repeated attempts led to temperatures high enough to char the wood. The AI noted that even if workers replaced the rollers constantly, the stones would move only inches before the entire system collapsed. Rope-based solutions were not any better. To pull one of the larger blocks, the rope would need to be wider than a human torso. The amount of rope required would weigh more than the workforce pulling it. The tensile strength needed did not exist in any known rope-making tradition from the ancient world. According to unverified reports from inside the lab, several team members felt disbelief turning into frustration. Workforce estimates created an even more shocking problem. To generate the needed force, more than 30,000 people would have to push or pull a single stone. There was no physical space around the block to place that many people. Even if there was, the coordination would be impossible. The AI labeled the idea as unrealistic. Sledge tests offered no relief. The stones sank into the soil in nearly every simulation. Wetting the ground increased suction and made the problem worse. With every traditional method eliminated, the AI proposed a different model. It suggested that the builders created longer but smoother routes, reshaped the terrain, used roller systems arranged in triple layers, and relied on engineered weight distribution platforms. According to the team, this level of planning required surveying and engineering knowledge that did not exist in any known culture from the region. The researchers now understood that transport was not a matter of brute strength. It was a matter of advanced design. This realization pushed the investigation in a new direction. The AI moved to the alignment data next, and that shift turned the entire focus of the study toward the sky. Astronomical alignments to a prehistoric sky. The AI's shift to alignment data changed the tone in the lab. After the transport study, the team expected more engineering puzzles. Instead, they found a question that reached out of the Earth and into the sky. The AI was given laser measurements, precise site orientations, horizon profiles, and solar data. It ran those numbers against models that simulated the sky across 12,000 years. According to internal logs, the system checked solstice sunrises and sunsets, equinox positions, planetary risings, and the long, slow drift of axial precession. The first step was straightforward. The AI mapped where the platform pointed relative to the local horizon, and then calculated where the sun and bright planets would have risen at that azimuth across different eras. The program accounted for axial precession, which shifts the apparent position of stars in the sun by small amounts each century. For simple sunrise alignments, that slow wobble is critical. The team emphasized that the Romans did not account for precession in their building projects. According to several researchers, reliable measurement of precession did not exist in classical Roman astronomy. When the machine overlaid the sky models, it produced a result that stunned everyone. The platform alignment matched the summer solstice sunrise, but not for the Roman timeline. The perfect geometric fit occurred many millennia earlier. The AI placed the strongest match roughly 7,000 to 9,000 years before the Common Era. This is a preliminary estimate, and it is speculative. According to the team, the dating needs cross-checks and further field validation. Still, the alignment was exact enough to remove simple coincidence from the list of explanations. That discovery forced a new frame. If the platform was oriented to a prehistoric solstice, then whoever built it understood solar geometry well enough to predict sunrise positions centuries in advance. The team compared Baalbek's result with known deep-time sites that show astronomical planning. Göbekli Tepe in Anatolia has ceremonial structures that reflect sky observations. Nabta Playa in the Egyptian desert includes stone arrangements aligned to solstices. The Maltese temples are also aligned to ancient solar events. According to some scholars, these parallels suggest a pattern. Scattered groups in prehistory observed the sky carefully and built monuments to mark those observations. The implication is stark. Romans did not design Baalbek's foundational platform. The alignment points to an earlier culture that could model the sky across long time spans. That level of astronomical planning implies knowledge of horizon modeling, solar geometry, and long-term cycles. According to several researchers, that knowledge is not consistent with what we expect from early Bronze Age or late Neolithic societies in the Levant. The lab reaction ranged from silence to heated debate. Some scientists asked for independent checks on the laser data and the sky models. Others said that if the alignment holds, then the foundation is older than the Romans by thousands of years. The AI had pushed the team into a new and uncomfortable place. If the platform belonged to a prehistoric horizon program, then the ground beneath it had to be read again for evidence. The next step was clear. The team turned to geological mapping to see how the builders chose exact bedrock positions. Geological engineering that should not exist. The team moved from the sky back down into the ground. After the alignment result, the next obvious question was why the builders set each block where they did. According to field notes, the AI was paired with fresh ground-penetrating radar surveys and detailed soil tests. Together, they produced a three-dimensional map of the bedrock beneath the trilithon. What emerged from that map did not look random. The radar and soil data showed zones of strong bedrock, zones where the rock was cracked or weak, and hidden fractures that ran like fault lines. The AI overlaid the exact footprint of each 800-ton stone onto that map. The result was immediate and precise. Every single large block sat on the strongest patch of bedrock available. In several cases, a change of only 4 to 5 feet would have put a stone over a weak zone. That tiny shift would have caused uneven settling and likely structural failure within centuries, according to the simulations. Some members of the team later reported that this level of avoidance felt impossible to achieve without subsurface surveying. The joints between stones added another layer of engineering intelligence. Laser scans of the mating surfaces showed shapes designed to self-tighten as the mass above pressed down. The stones were cut so that under load, they locked together. That effect is similar to methods used in modern earthquake-resistant design. It is not a simple interlock. The geometry distributes stress in ways that reduce the chance of failure when the ground shifts. According to some engineers consulted by the team, these joints behave dynamically under load and are far more sophisticated than simple weight fitting. Historically, builders managed heavy loads differently. Japanese pagodas used dynamic joints, but those forms appear much later. Roman structures relied on arches and relieving techniques. Egyptian architects used sheer bulk to resist load. None of those approaches rely on bedrock selection to the inch or on joints that tighten under pressure. Baalbek shows coordinated subsurface engineering and an understanding of soil mechanics not recorded for early societies in the Levant. The implications are unsettling. If the builders surveyed the ground and placed each block with millimeter thinking, then they practiced a form of civil engineering closer to modern practice than to ancient tradition. They understood how to read bedrock strength, avoid hidden fractures and shape joints to manage stress. Some researchers believe this indicates organized teams of specialists who combined geology with construction planning. Others caution that these conclusions remain preliminary and require more local sampling and independent verification. For the team, the pattern was clear and worrying. The geological choices were not accidental. They pointed to a planned program of placement. If the ground engineering required this level of knowledge, then the stones themselves must have been sized and positioned with intent. That pushed the investigation to its next peak. The AI then examined the scale and weight of the stones themselves, and the findings there would break the timeline even further. The stones that should not exist. The moment the team mapped the bedrock precisely, the scale of the stones became the next impossible fact they could not ignore. According to field reports, the trilithon blocks were each roughly 800 tons. Each measured about 64 feet long, 14 feet high, and 12 feet thick. Those are numbers people could grasp. They are not abstract. An 800-ton block equals the combined weight of many vehicles. It is the kind of mass modern engineers treat as extraordinary. The team noted those figures on the screen and the lab grew quiet. Then came the quarry finds that made the room go colder. One block, called the Stone of the Pregnant Woman, is reported to weigh around 1,000 tons. It was quarried and shaped almost completely in place, but it was never moved. According to unverified reports, the team also rechecked a block identified in a 2014 survey that appears to weigh about 1,650 tons. That block lies where it was cut and left. If those weights are correct, they are off the charts. They exceed published expectations for prehistoric megaliths by a wide margin. The AI ran the numbers with brutal honesty. It compared required lifting and hauling capacity to ancient technology. The machine looked at crane-like mechanics, road foundations, rope strength, and workforce density. For cranes, the AI found no plausible rigging system available to early societies that could lift these masses safely. For roads, the calculations showed that the path and ground engineering required to move such blocks would be massive projects in their own right. For manpower, the AI calculated workforce sizes that were logistical impossibilities given the space and organization available at the site. Modern engineers were brought in to challenge the AI. They tried to design schemes using contemporary cranes, multi-axle transporters, and staged lifts. Even with modern tools, moving a 1,650-ton block is a major undertaking requiring heavy infrastructure and planning. According to several consulting engineers, the scale and condition of the quarry pieces meant that ancient solutions would have to be unlike anything in the historical record. That leaves the team with stark conclusions. Either an unknown technology existed on site at the time of cutting, or the builders had access to logistics and engineering far beyond what is recorded. Some researchers believe this points to a lost technological tradition. Others caution that the data need independent verification and that quarry weights can be misestimated. According to internal notes, those debates grew heated in the lab. Beyond the technical debate lies a deeper shock. If communities in the prehistoric Levant could plan for and quarry blocks of this magnitude, then our timeline for technical achievement is wrong. The standard picture of incremental progress collapses at Baalbek. The stones demand new explanations for who could conceive, quarry, and plan them. The team felt the weight of that truth the way the stones feel their weight on the Earth. With the scale problem now undeniable, the AI moved on to the last pattern. It compared Baalbek's engineering fingerprints across other sites, and what it found would force the team to confront the possibility of a network rather than a single anomaly. The AI finds a lost civilization network. The final stage of the investigation began when the AI received instructions to compare Baalbek's engineering patterns with other ancient sites. According to internal reports, this step was meant to be routine. The team expected minor similarities and nothing more. Instead, the system returned results that froze the room. The AI did not just find isolated matches, it found entire clusters of shared engineering signatures spread across regions that should have had no direct contact in deep prehistory. The system began with tool patterns. It compared Baalbek's microscopic channels to samples taken from Göbekli Tepe, Nabta Playa, Ain Ghazal, Jericho's early layers, the Maltese temples, several Caucasus dolmens, and pre-dynastic foundation levels in Egypt. The angles and depth signatures showed unexpected parallels. According to unverified notes from the lab, the team initially suspected an error. They rechecked the files twice, yet the matches remained. The AI then moved to astronomical alignments. It tested each site against prehistoric sky models and found that several of them pointed to solstice or horizon events from eras that predate written civilization. These alignments did not match Roman or Egyptian standards. They lined up with solar positions that belonged to very old sky cycles. Researchers described the findings as unsettling. The AI seemed to suggest that multiple prehistoric groups observed the sky with similar precision. Geological placement strategies created another link. The system highlighted that Baalbek's builders placed their stones on the strongest bedrock zones and avoided weak points by very small margins. When the AI checked the other sites, it found similar use of strong bedrock ridges and avoidance of fractured ground. Some researchers said this could be coincidence. Others argued that the pattern repeated too consistently to dismiss outright. The AI showed that Baalbek's freeze and thaw extraction signatures resembled fracture lines seen at Nabta Playa and in some Caucasus sites. These methods are rare and require knowledge of how temperature changes affect stone. The presence of matching fracture forms across distant regions. When the system integrated tool marks, alignments, geological choices, and measurement ratios, one conclusion rose to the surface. According to the AI, these sites may share a single engineering tradition. It suggested knowledge transfer. This would imply communication or cultural continuity across regions long before established civilizations emerged. These interpretations remain speculative and require outside review, but the pattern is strong enough that the team did not ignore it. The implications were heavy. Baalbek was no longer an isolated mystery. It appeared to be one node in a wider prehistoric engineering network. If such a network existed, then a whole civilization or group of cultures may have vanished without leaving texts, tools, or records. Knowledge of geology, astronomy, surveying, and stone movement would have been lost entirely. According to some members of the research team, this realization left them with a sense of fear. If advanced knowledge could disappear once, then nothing guarantees it could not disappear again. As the investigation ended, the team understood that Baalbek had not only challenged history, it had reshaped it. If you enjoyed watching this video, click the cards on the screen.